So we are given a 10-meter tall cooling tower with a 100 meter squared cross section. So A equal to 100 meters squared. And the cooling tower has diagonal slats over which falling water comes in contact with counterflowing air. The diagonal slats provide 5 meters squared of water-air contact area per cubic meter. So lowercase a would be equal to 5 meters squared per meter cubed with negligible drop in air pressure. So the total contact area would be equal to A times the total volume of the cooling tower. Oops. So we have that equal to 5 meter squared per meter cubed times 10 meter, which is the height, and 100 meter squared, which is the cross-section area. So the total contact area of air and water is 5,000 meters squared. And then the heat transfer from air to water film flowing down the diagonal slat of the cooling tower is well correlated by the equation where we have Nusselt number equal to 0.6 times Reynolds number to the 1/2 times Prandtl number to the 1/3. And we have 50 kilograms of water is fed to the top of the tower. So given that, we can calculate the superficial mass flow rate of water vapor. Mass flow rate. G water vapor equal to 50 kilograms per second times the area, which is 100 meters squared, equal to 0.5 kilograms per meter squared times second. And the temperature is 70 degrees C. Then air is fed to the bottom at superficial velocity of 5 meters per second, and it exits the top of the tower at 40 degrees C and 90% relative humidity. Under these conditions, the air-water heat transfer coefficient was measured to be H equal to 10 watts per meter squared Kelvin. For simplicity, the Lewis number of air-water mixture would be 1. So the first part of the exam is to derive and explain the differential equations governing air temperature, water temperature, and water mole fraction in air. So what I would do here is to take a look at a very small section with a thickness of dz. We will have water coming in from the top and coming out from the bottom, with temperature is Tw and enthalpy is Hw. Then air coming from the bottom, coming out from the top, and we have Ta as air temperature, and Y is mole fraction of water vapor. And then I will choose the direction from top to bottom as positive direction for position. And then I will take a look at energy balance of the system. Okay, so let's zoom out the interface between water and air. So here we have water, here we have air. Right here at the interface, we will have the concentration of water, and here we're gonna have the concentration of water as CW infinity. And apparently concentration of water at the interface would be greater than concentration of water at infinity. So for the change in enthalpy of water, it would be equal to heat capacity of water times mass flow rate of water times area times change in temperature. The change in temperature of water depends on two factors. The first one is evaporation of water, and the second one is heat transfer to or from air. We don't know that yet. And then that would be equal to the area of contact per volume, lowercase a times volume, which is A times dz, or area times height, times the difference in concentration of water at the interface and at infinity. Times Kc times lambda. So lambda is heat of vaporization of water when it goes from liquid to vapor, and the value of lambda is 40,660 joule per mole. And then, as I said here, the concentration of water at the interface is greater than the concentration of water at infinity. So the value of this would be a positive number. So the right-hand side is a positive number, but the left-hand side, because this is a cooling tower, so we can easily say that the temperature of water coming out right here is lower than the temperature of water coming in. So the change in water temperature from top to bottom would be a negative number. So the left hand side is a negative number. So what I would do is to add a negative sign in front of CWI minus CW infinity to make the right hand side a negative number. And then because the change in enthalpy of water is also depends on the heat transfer from or to air, so I'm gonna add that term as well, which is H times TA minus T water. The reason why we have a positive sign right here, because let's say if we have TA, if we have the temperature of air is greater than the temperature of water, then we would have the heat transfer from air to temperature, so air to water. And so let's say we have the temperature of air is greater than the temperature of water, so we will have heat transfer from air to water, so the temperature of water is increased from top to bottom. So dTW would be a positive number, so the left hand side is a positive number, and this portion is also positive, so it makes sense, therefore it should be a positive sign right there. So this is what we have so far, and I will call this equation number 1. And then next we will take a look at, I'm gonna draw it again, a small section, height of dz, where water coming in and then water coming out, and air coming in from the bottom, air coming out. So we have steady state. So the difference in enthalpy of water and enthalpy of air would be 0. Therefore, we have change in enthalpy of air would be equal to change in enthalpy of water. And then this would be equal to the mass flow rate of air, which is G times CPA, which is the heat capacity of air, times the area, times change in temperature of air, which would be equal to DHW, which is the change in enthalpy of water. So it would be equal to the equation number 1 here, because this would be equal to the right hand side of equation number 1. And then we also have that the total mass flow rate would be equal to the mass flow rate of air plus mass flow rate of water vapor. So this would be, we have GA is 5 meter per second. Next, I would calculate the mass flow rate of air from the bottom. It would be equal to cross-sectional area times mass flow rate of air, and it would be equal to density times volumetric flow rate, and it would be equal to pressure times molecular weight of air over RT times velocity times cross-sectional area. So we have this and this canceled out. So I would have mass flow rate of air equal to pressure times molecular weight of air over RT times velocity. And then now I'm going to calculate the average molecular weight. It would be equal to mass flow rate of water vapor plus mass flow rate of air divided by mass flow rate of water vapor divided by molecular weight of water plus mass flow rate of air divided by mass flow rate of water vapor. So we basically have total mass right here divided by total moles. So we have average molecular weight. And then now I'm gonna calculate the mass flow rate of water vapor using this equation where we have mass flow rate of water divided by molecular weight of water equal to mole fraction of water vapor times the total mass flow rate divided by average molecular weight. So mass flow rate of water would be mole fraction of water vapor times total mass flow rate divided by average molecular weight times molecular weight of water. And then I would have the area times total mass flow rate divided by average molecular weight times dy, which is change in mole fraction of water, equal to area of contact per volume, A, times volume times Kc times difference in concentration of water at the interface minus the concentration of water at infinity. We have this equal to the water vapor pressure at that temperature divided by RT, and this would be equal to mole fraction of water times P over RT. So the next thing I would do is find the value of Kc. So what we have is we were given an equation where Nusselt number equal to 1.6 times Reynolds number to the 1/2 times Prandtl number to the 1/3. Therefore, we would have Sherwood number equal to 1/6 times Reynolds number times Schmidt number to the 1/3. I would take the equation, would take the second equation divided by the first equation, and then I also have the heat mass transfer analysis here. Where Lewis number is equal to Schmidt number divided by Prandtl number, which would be equal to kinematic viscosity divided by density times diffusion coefficient DAB divided by kinematic viscosity times density times heat capacity divided by density times thermal conductivity. So it would be simplified to thermal conductivity divided by density times heat capacity times diffusion coefficient, DAB. So having that, we will have thermal conductivity of air is 0.03 watt per meter Kelvin. Density of air is 0.2 kilograms per meter cubed. Diffusion coefficient of air and water would be 3 times 10 to the negative 5 meters squared per second, and heat capacity is 1,000 joule per kilogram. So if I substitute these values that I found online to this equation, we will have the Lewis number approximately equal to 1. And then the next thing I would do, as I said before, I'm gonna take this equation divided by this equation. So what we would get is, I'm gonna go all the way down here. What we would get is Sherwood number divided by Nusselt number equal to Kc times characteristic dimension, which is D, divided by DAB, which is diffusion coefficient, divided by heat transfer coefficient times D divided by thermal conductivity, which is equal to Kc over H times K over DAB, and that equal to the right hand side here. If you take this divided by this, these would be cancelled out, these would be cancelled out. So what's left is Schmidt number divided by Prandtl number altogether to the negative to the 1/3, and this is equal to Lewis number to the 1/3. And then we also have this equal to Kc over H times density times heat capacity times Lewis number equal to Lewis number to the 1/3. So I'm gonna substitute this equation where we have Kc times rho times Cp equal to H times Lewis number to the 2/3, but we have this equal to 1. I'm gonna substitute this into equation number 1. Equation number 1 is right here, and I'm gonna substitute the equation that we just derived to H, and then we will have what we need. So I will write the full equation one more time, where we have the heat capacity of water times the mass flow rate of water times the area times change in temperature equal to area of contact per volume A times the total volume of their cooling tower times negative difference in concentration of water at intersection at the interface minus concentration of water at infinity times Kc times lambda plus H. We have H equal to Kc times rho times Cp times difference in temperature of air minus temperature of water. And yeah, that's it for question